Okay, thanks very much. This is joint work with Paul Dütting and Tim Roughgarden. And I see a few familiar faces from yesterday's tutorial. I won't say a lot of new things, so I hope you won't be too bored. Okay. Okay, so we're going to be talking about contracts. The purpose of contracts is to align the interests of different players in order to enable them to exploit gains from cooperation. There's some deep microeconomic theory on this topic, on contract design, awarded the 2016 Nobel Prize in Economics. And there are also tons of applications. So the prize announcement says modern economies are held together by innumerable contracts, so like really stressing the practical importance. Here are a few applications that probably everybody here has encountered at some point. So employment contracts, VC investment contracts, insurance, freelance if you're writing a book, or something like this, government procurement, and so on. So contracts are really everywhere, and what is happening in recent years is that a lot of these applications have kind of online parallels and or are increasing in complexity. So for example, we have these crowdsourcing platforms and platforms for freelancers. We have online marketing, affiliated marketing, complex supply chains, and so on. So I think this is kind of a really good time for this community to be looking at contracts, both because they're relevant to applications that interest us, and also because the algorithmic approach is becoming more relevant as these things become more computational. Okay, so the kind of high-level agenda of that this paper falls under is what can we learn about contract design through the algorithmic lens. Okay, and we have kind of several things that usually the algorithmic lens has been really helpful with in other areas of AGT. One of them is providing robust alternatives to average case or Bayesian analysis, enabling us to take an approximation approach when optimal solutions are too complex or otherwise unrealistic, inappropriate, and so on. And of course, to address complexity issues, today's talk will be about the first two, and the third one on complexity, we address this in some ongoing work. Okay, so as I mentioned in the beginning, I gave a tutorial on this with Paul yesterday, and there's a lot more information there. We're kind of excited about this direction, and so if you're interested, please take a look at the website. Okay. So related work, this is definitely not an area that we looked at AGT nearly as much as as actions or as signaling, but there have been works. I just put them here on this slide. I mentioned maybe one of the first ones, which is work of Babayev, Feldman, and Nissan. And in this EC, there are actually two other talks on contracts. Okay. So let's start to be more concrete. Let me show you an example of what I mean by contract setting. This is a basic setting. It only has two players. Okay, throughout this talk, I'm just going to be talking about two players, and I'll be referring to them as principal and agent. Okay, so imagine that you are a website owner. You're the principal, and you want to hire a marketing agent that will do some work and attract visitors to your website. Okay, so the marketing agent obviously has to put in effort in order to attract good visitors to your website. And the more effort she puts in, maybe she'll get you better visitors. But notice that although she bears the cost of her actions, okay, she does the work, she doesn't enjoy the rewards, right? The rewards are something that's enjoyed by the principal. So we have to incentivize her. We have to design a contract as the principal that will incentivize her to invest the right amount of effort, okay? The amount of effort that will balance the expected gains that I get as a principal minus whatever I have to pay the agent. Okay, so there are two very important defining features of this whole model that I want you to notice from this example. The first one is that the whole point of hiring an agent is that you don't want to track her every move. You basically want to her to do the work, and then you will get that. You will see the outcomes. You will see the visitors coming to your website, this is known as hidden action. Okay, so the contract is not going to refer to the actions of the agent. The actions are hidden from the principal. Principal only sees the outcomes of the action. Okay, another name for this is moral hazard. The second defining feature is that in this model, money is flowing from the principal, from the website owner to the agent. Okay, so you hire somebody, you pay them, you don't charge them. This kind of makes sense. Okay, and the name for this is limited liability. And these are the two most important features that make this model different than other familiar models. Okay, so just to very quickly say what are the main differences from mechanism design, auction design, and from signaling. So in mechanism design, agents will have hidden types, right? They have something they're willing to pay for the items, and this is hidden. In contracts, we don't have types for the agents. In this case, one agent. In signaling, the principal is the more informed side, the more informed player, maybe selling something and knows the nature of whatever they're selling. Okay, in contracts, it's the other way around. The principal is less informed about what? About these hidden actions, right? Whatever the action that was taken, that's the kind of private information is not known to the principal. Okay, good. Here is an overview of our results. We study the model of Holmstrom, a classic fundamental model with these two players that I informally described. And the two results that we show are, first of all, we give a new robustness maximum justification for why we tend to see simple linear contracts in practice, even though they're not optimal. And this is kind of maybe standing on the shoulders of a work by Gabriel Carroll, and I'll talk a little bit about the differences. And then the second result that we show is we apply the approximation approach, and we look at simple contracts, again, linear contracts, and we analyze what they can get us in terms of approximation guarantees when we compare to the optimal contract, which is complex. What we show is that they're actually going to perform quite well, except for in pathological cases. Our approximation guarantees are tight. Okay, they're tight for even a larger class of simple contracts, known as monotone contracts. Okay. Questions so far? Okay. So here's the model more formally. Probably I won't have time to show you a lot of the results because I think for many here in the audience the model is maybe not familiar. So I'll show you the model and then I'll talk about the results depending on how much time I have. Okay, so here's a setting. The setting has two parameters, n and m. Okay, the number of actions that the agent has is n, and every action has a cost. Okay, denoted by C1 to Cn. The costs are, without loss of generality, increasing. Okay, I'm also kind of normalizing the first cost to be 0. That kind of means we can forget about things like about individual rationality because the agent can always kind of go to the action that doesn't cost her anything. Okay, now the principal has rewards, R1 to Rm. Again, they're ordered in increasing order. Okay, and what's the connection between the actions and the rewards? Well, there is a distribution. For every action I, there's a distribution. I'm denoting it by capital F sub I. This is sometimes known as technology. And I'm going to denote the expected reward. This is a distribution over reward. The rewards, the expected reward is R, capital R sub I. And I'm going to assume that the rewards are increasing. This kind of makes sense. If I have an action that is very costly and doesn't get me as much reward as maybe a less costly action, then it's kind of not dominated, and I can assume that we don't have that. Great. Okay, so this is the whole model. And what's a contract? A contract will be transfers that the principal gives the agent depending on what the reward is that the principal sees. Okay, so notice this reflects the two defining features that we talked about informally before, because the transfers depend not on the action that is taken, but on the reward that the principal sees. Okay, the actions are hidden; they can't be contracted over. And the second thing is that these transfers are non-negative. Okay, and this is exactly this limited liability assumption that that is a second defining feature. Great. Let me show you a quick example. Here's an example where the number of actions is 3. The number of rewards is 4. Okay, m equals 4. And you can see that each action kind of maps to this distribution over the outcomes. Okay, and you can see that if I compute the expected rewards, they're increasing as I assumed. And here's a contract. Well, it will map every reward to some transfer, maybe pay 0 if the reward is 0, and so on. Okay, and this example is about this website owner and marketing agent that we saw before. Okay. So what is the design problem here? Okay, we know the setting. What is the design problem? We're looking at it from the principal's point of view. And we're trying to optimize the principal's expected payoff, okay, from action AI, where action AI will be what the agent wants to take given the contract. Okay, so action AI will be whatever maximizes the expected utility of the agent. So it's basically something we know well, right? It's optimization problem subject to incentive compatibility constraints. Okay, incentive compatibility constraints means that the action is chosen by the agent so that it will maximize her expected utility. Okay, just to kind of show what I mean by expected payoff, what I'm trying to maximize for the principal, I mean the expected reward from the action that the agent takes minus whatever the principal is transferring to the agent. Okay, so this is the expectation. Taking every reward that can happen, what is transferred, and this is just the expected payment. And then for the agent, it's the other way around. So trying to maximize the expected payments minus the cost that she has to pay if she takes a certain action. Okay, so in our example, the way this looks is, let's first look at it from the agent's perspective. So she can let's fix the contract, and then the agent does the following kind of mental calculation. She says, okay, what's the expected transfer that I get for each one of these actions, each one of these effort levels? Okay, and then she takes the expected payment, and she subtracts her cost. So for example, for the highest effort level here, she has 3.4 minus her cost, which is 2. Okay, and she does this for every one of the actions, and then she picks the action that maximizes her utility. Okay, so in this case, she will put in the highest level of effort possible. Great, and now go to the principal's perspective. So the principal, everything is kind of known, so she can anticipate that if this is the contract, then the agent will be putting in high effort. And so she knows exactly what this contract is getting her in terms of expected payoff, getting the principal in terms of expected payoff, because she knows the expected rewards. Okay, she knows what the expected transfers are, right? This is from the previous slide. So for example, she knows it's 3.4 for the highest effort. Okay, and now she subtracts, and she can see that, for example, this particular contract will get her 3.8 in expected payoff. And the question is how to optimize this. What contract will maximize this? Okay, and there's actually a simple LP-based solution to this design problem. Here's an observation. You can compute the optimal contract by solving n linear programs, one per action. And I wrote down the linear program that achieves this. Actually, I think I won't go into the details, but basically you minimize. What you want to do is you want to go over every action, find out through this linear program what is the minimum expected transfer you have to give your agent in order for her to take this action. And then you, exactly like we did on the previous slide, you can know what your expected payoff is, and then you know what you take the maximum. This is the best contract. Okay, let me skip this. I want to point out two problems with this approach. The first one is that, of course, in order to do this, to write this linear program, you need to know this matrix of distributions very precisely. And the second thing is that whatever comes out of the LP might kind of seem arbitrary and not make much economic sense. For example, you don't even necessarily have the natural property you would want is monotonicity, that the more reward that the agent gets for you, the more you pay her as a principal, the more you transfer to her. And this doesn't necessarily happen in this approach. Okay, so our two results kind of address these two problems. The first result will address the problem of not knowing the distributions. So the first result is robust optimality. I'm going to be talking, the result refers to linear contracts. A linear contract is really simple. It just is defined by one parameter alpha. And basically, as a principal, whatever reward I give alpha times this reward to the agent. Okay, really simple contract. You can calculate what is the expected utility from an action from an agent under a linear contract with parameter alpha. And same thing for the principal. Okay, and you can see that these two expressions depend only on the expected reward. Okay, there's no dependence on the distributions. So this already kind of gives you the hint that linear contracts are very robust. Okay, and they're super popular in practice. Okay, this is why they're of interest. So in microeconomics, this has, of course, been noticed, this gap between what's happening in practice and the optimal thing that comes out of the linear program. Okay, and Milgram and Holmstrom kind of posed this as open problem to find a formulation, and Carroll found a formulation, the first formulation, showing that linear contracts are optimal in the worst case over unknown extra actions that might be available to the agent. So this is a breakthrough result. There are other ways in which we might want to show alternative formulations of what it means for linear contracts to be robustly optimal. Okay, and this is what we do. We take a standard CS way of formulating uncertainty about distributions. Okay, when you're not sure about the distribution, you might assume that you only knew the first moment. Okay, this goes back even to SCARF 58. And what would this mean in our setting? So instead of knowing this whole setting that we saw before, you would only know, right, everything now is unknown except for the expected rewards. Okay, and here's our result. So the theorem says that if you're given a contract setting with unknown distributions but with known expectations, like we saw in the previous slide, then a linear contract will be optimal in the worst case over all the compatible distributions with these known expectations. Okay, so basically, same conclusion as Carroll's work, but in a very different assumption of what you know. Okay, so we think it kind of strengthens this idea that linear contracts are robust. And it also really nicely captures the intuition that, let's say all you know is these expected rewards, so you just know enough to design basically the best linear contract. Well, we saw that this linear contract, whatever it gives the principal, it only depends on the expectations. So if you know only this thing, optimize for that. Okay, this is the intuition behind our result. So I will skip the proof overview. I will very quickly show you kind of an informal version of our result, and then I'll summarize. So here's the second thing that we do in this paper about simple linear contracts. We look at what is the fraction of the optimal payoff that is achievable by a simple contract. And here's our result informally. So we show that linear contracts will achieve a constant approximation to the optimum, except in pathological settings, which have all of the following together. They have many actions. They have a very big spread of the expected rewards, basically exponentially exploding. And they have a very big spread of costs of these actions, also exponentially exploding. And if that's not the case, then you can be kind of sure that the linear contract will work well. Okay, so I think I'm out of time. Okay, so here's my summary. High-level message, contract theory can be an interesting new frontier for AGT. Algorithmic approach can provide new insights. For example, that if you only have moment information, optimize for that. You can expect linear to work well, except in really weird cases, and opportunities for new success stories. And that's it. Happy to take questions.